I'm Dr. Vibha Tiwari, Professor in Electronics Engineering Department. आज हम डिकेड काउंटर पढ़ेंगे. काउंटर क्या होते हैं? काउंटर काउंट करते हैं, बाइनरी काउंटिंग करते हैं from 0 to the required number. So counters are basically of two types, asynchronous and synchronous. Asynchronous के केस में जो फर्स्ट फ्लिप फ्लॉप होता है उसको मेन क्लॉक सिग्नल दी जाती है और जो सब्सिक्वेंट फ्लिप फ्लॉप्स होते हैं उनको क्लॉक सिग्नल दी जाती है इनके प्रीवियस फ्लिप फ्लॉप के आउटपुट से, जैसा आप यहाँ देख सकते हैं. सिंक्रोनस काउंटर्स में क्या होता है, ये जो क्लॉक सिग्नल है ये कॉमनली सारे फ्लिप फ्लॉप्स को अप्लाई की जाती है. तो हम बात करेंगे डिकेड काउंटर असिंक्रोनस काउंटर के थ्रू. ये 3 बिट बाइनरी काउंटिंग है जहाँ पे मैंने आउटपुट्स यहाँ लिखे हुए हैं एज Q0. ये सेकेंड फ्लिप फ्लॉप का आउटपुट है Q1, तो हियर आई हैव रिटन Q1 एंड द थर्ड flip flop output is Q2, it's written Q2. So whenever the clock signal is applied to first flip flop, you can see this is a negative edge triggered flip flop. That means whenever in a clock signal a negative edge will come, then it will change its state. Now here in JK flip flops are used, so we'll see what is the truth table of JK flip flop. You have a clock signal, J and K input signal and output Qn plus 1. Qn plus 1 signifies what will be the next state. So a JK flip flop works only when you have a clock signal as 1. Then only you will get some kind of a output. So JK, when they are 0 0, you get the output as same as previous, so it's written Qn. And when the JK inputs are 0 and 1, then you get a output as 0. When it is 1 0, you get a output as 1, and in case of 1 1, you get a toggled output. Toggled output means if the earlier state was 1, now you'll get 0. If it was 0, you'll get 1. So it will keep on toggling. This is what we have used. In this particular counter, to a JK input will give 1 1. Whenever the clock, negative clock edge will come and inputs are 1 1, you will get the toggled output. So here you will see this is what is happening. A clock signal with a negative edge triggered. These are the negative edges of the clock signal. Whenever a negative edge is coming, the first flip flop output Q0 is changing its state from 0 to 1 and so on. So at every clock edge, negative edge is changing its state. This is the output of first flip flop. Now this output of first flip flop is given as the input to the second. This output of first flip flop is given as the clock signal of the next flip flop. So that next flip flop again has a J and K input set as 1. So whenever the negative edge will come as a clock signal to second flip flop, it will change its state. So you can see here it's changing its state 0 to 1, and again whenever the negative clock edge is coming, it's changing its state from 1 to 0. This particular clock signal is this particular output Q1 is applied as a clock signal to the third flip flop. So the same way it will behave. JK inputs are 1, so they will toggle when there is a negative edge at the clock input. So whenever there is a negative edge, then in that case it will change its output, the third flip flop, from 0 to 1. So this is how it's working. We'll see the binary numbers, how counting is done. 0 0 0 is nothing but 0. 0 0 1 is a decimal number 1. 0 1 0 is 2. 0 1 1 is 3. 1 0 0 is 4, 1 0 1 1 is 5. It will go up to counting up to 6, 7, and once it reaches 7, it comes back to 0. So this is how it keeps on working. Now coming to the decade counter about which we need to talk. So we have a basic building block. Now we'll understand the decade counter. Decade, the word says that means it has 10 states. It needs to count only up to 10 states. So we'll be taking 4-bit binary counter. Now since this is 4-bit and we know that 2 power 4 is 16, that means a 4-bit binary counter will count from 0 to 15 or 4 zeros in binary up to 4 ones, right? This is what will be done normally by a 4-bit binary counter. But what is our requirement? We need to count only up to 10 states, starting from all zeros. That means a decimal number 0 to 9. And a binary equivalent of 9 is 1, 0, 0, 1. We want this much only. We don't want this particular state, that is 1010, a decimal equivalent of 10. This is not required. So whenever the counter counts up and reaches to 1010, we want that all the flip-flops must be cleared. So this one is at Q1 and this particular one is at Q3. That means whenever Q1 and Q3 are both 1, we want that all the flip-flop must be cleared. And this clear signal in flip-flop is a negative signal. So this clear signal, we want that at the clear input a 0 should be given, then all the flip-flops must be cleared. So how it's possible? This is possible with the help of NAND gate. We know the truth table of NAND gate. When all inputs are 1, then in that case a 0 is received. So this is what we'll use and we'll implement our decade counter. So you can see this is the decade counter with 4 flip-flops, flip-flop number 1, 2, 3 and 4. There is a input as J and K in all, to which a logic 1 is applied. Then the flip-flops have outputs labeled as Q0, Q0 bar, Q1, Q1 bar, Q2, Q2 bar, Q3 and Q3 bar. Apart from that, there is a clear signal, CL bar. CL bar will work to clear all the flip-flop states when a 0 is applied to this particular flip-flop. So herein you can see the output of Q1 and Q3, both are taken and applied to a NAND gate. This is our NAND gate. Whenever both the inputs are 1, then only you will get a 0, and this 0 is given as an input to the CL bar, which will lead to clearing all the flip-flops. And when this situation will come, this situation will come when, in the case, this situation will come when you have this particular state 1010. So this is the output of Q1 and this is Q3. When both Q1 and Q3 are 1, 1, then in that case you will get a 0 over here, which will clear all the flip-flops, and your flip-flop is resetted to the initial state, all zeros. So this decade counter will count from all zeros up to 1001, and this is binary equivalent of number 9. So this is all about the decade counter. Thank you.